Vertex form. We've been working with equations in vertex form, and we just a few moments ago wrote an equation given a graph, given some information from a graph. Now let's go the other way. Let's graph equations given the fact that we've got something written in vertex form. Now, I will tell you, be honest with you, you could actually just put this in the calculator right there. It would graph it for you. But let's talk about the elements of it, and we'll actually graph it by a couple of points, or we'll get started there. So here's our vertex form. Y equals A times X minus H, and H there is the X coordinate of the vertex, plus K, and K is the Y coordinate of the vertex. So let's look at what we have in this first equation and see if we can't get a little bit of information that's going to let us graph, and then we'll look at the second, and then we'll move over to some graphing, GeoGebra graphing software, and we're going to graph these things. All right, so question, what's the vertex in this equation of this quadratic equation right here? Well, if this is X minus H, and that is 3, and if K is the Y coordinate, and that's negative 2, then I've got a vertex at 3, negative 2. So my vertex of this parabola is going to be at 3, negative 2. And 3 is also the axis, when x is equal to 3, I should say. That's the axis of symmetry of that graph, which means that any point on that graph, for any value, well, they're going to be equidistant from, any y value is going to be equidistant from that axis of symmetry, and it will probably be a little bit better to see once we get on the graphic. Now, I need probably one other point on this graph, because that'll tell me how many units away I am from the axis of symmetry. So let's just say that what happens when x is equal to 1? So if I just go y equals 1 minus 3 squared minus 2, what's y going to equal? So here we got negative 2 squared minus 2, and y then is going to equal 4 minus 2, which is equal to 2. So when x is 1, y is 2. And we're going to use these 2 points to help us graph this. All right, let's look on this other one before we move to the graph paper. Now again, what do we see here? Now right here I see a plus 1. But remember, this is x minus h. So this is really y equals x minus negative 1, writing 2 for some reason, negative 1 squared. And then what about out here for k? Well, there's nothing there, so it's 0. So my vertex on this second equation is negative 1, 0. All right, now, what about when, let's get another point on here. What about when x is 1? And I do have an a value on this. If you look there, it's 0.25. So what about when x is 1? So I'd have x is equal to 0.25. X is 1 plus 1 squared. Y is equal to 0.25 times 2 squared. Well, 2 squared is 4. So x is equal to y is equal to 0.25 times 4, which means that y is equal, when x is 1, y is 1. And so I've got another point here of 1, 1. What's my axis of symmetry on this second equation? My axis of symmetry is going to be -1. All right, let's move over to some graphing software. Let's graph these. Let's remember, in fact, I'm going to jot them down myself right now. I've got a vertex of 3, -2, and then I've got another point at 1, 2. I've got an axis of symmetry at x equals 3. And then in my second equation, I've got a vertex of -1, 0. And I've got another point of 1, 1. And I've got an axis of symmetry at x equal -1. And let's use this information and see what we can find on the graph. All right, let's try graphing these, given some information that we determined there a few moments ago. So we determined that the vertex of that first equation was that when x is 3, y is -2. So let's go in here and let's put a point right there at 3, -2. All right, we got a point there. And we determined that there was another point on the graph that when x is 1, y was equal to 2. Okay, that looks okay. All right, now we are 2 units from the axis of symmetry to the left. So we can also expect to see a point, since that's the axis of symmetry, 2 units to the right from the axis of symmetry, which would be when x is 5, y is also equal to 2. All right. Now, let's just graph the function in that vertex form. So we got y equals x minus 3 squared minus 2. And Shazam, we line right up on the points that we had. So all we would have to do with a curved parabola line is just connect those points, which we let the software do for us. But there we go. All right, now let's look at the second one. The second one, we determined that when x is -1, the vertex, y is 0. So let's put a point right there. When x is -1, y is 0. And then we also determined that we had another point on the graph that when x is 1, y is 1. So we put a point there. Now, how many points on this horizontal line here where y is equal to 1 are we away from the axis of symmetry, where we're 2 units? So we can also expect to see a point 2 units to the left, so that when x is -3, y is also 1. Let's see if this holds true. So we got y equals 0.25 there we go, times x plus 1 squared. And Shazam, there we go again. So we've used the vertex, the knowledge that that's the axis of symmetry, found one point, used the axis of symmetry to find the second point. We've got a curved line. Now, look at what happened here. In this graph over here on the right-hand side, our first one, we did not have any dilation. In other words, we had a was equal to 1. But in our second graph, a was equal to 1/4, which means we were going to have a dilation. And since that dilation, the absolute value of it was between 0 and 1, in other words, it was 1/4, then we would say that the graph is compressed vertically. Now, this is where it always gets a little bit counterintuitive when you think about it being compressed, because it actually widened it out, made it wider, right? Well, think about it. If I took the ends of that graph and pushed down on them from the vertical axis, pushed down, then they would have a tendency to spread out. And therefore, we say the graph is compressed vertically. All right, well, that's pretty interesting. What else can you say but Shazam?